Good morning, everyone. Welcome to this workshop, Practical Machine Learning. It's the second day. We will touch the real machine learning thing. Before that, let's do a quick recap about what we talked yesterday. Yesterday, we talked the full episode. The first is about general introduction to machine learning. We talked the relationship between AI, machine learning, deep learning, and also the representative applications problem that cannot or can be but shouldn't be solved using machine learning. The second episode, we gave a fundamental of machine learning, including the main type of machine learning, that is supervised learning, unsupervised learning, and the machine learning workflow, and the representative libraries such as scikit-learn, Keras, TensorFlow, and PyTorch. The third is about the scientific data for machine learning. We covered what is big data and the type and the format of data storage format, and also the data structures that are used in machine learning and deep learning tasks. The fourth episode is about the data preparation for machine learning. We used the penguins dataset as an example and demonstrated how to handle missing values, outliers, and how to encode categorical variables. So I hope that you were able to pick up some key points from the lesson and also the hands-on exercises. Today, we will build on that and talk about two supervised learning tasks, that is classification and regression. Yesterday, from the comment, we got one very interesting comment. Let's come to the academic document. Statistical analysis of data not always properly taken into account in this Jupyter notebook. It is true. You always assume this normal distribution, but this is not always true. And so if such case happen, the concept like STD or IQR method have to be revised. I should say that totally agree with this. The default scaling tricks, Q-score or IQR, implicitly assume that the data is well behaved, often or quite close to Gaussian. But in practice, this might be not always true. If the distribution is skewed, such as we have very heavy-tailed distribution or multimode or categorical-like distribution, those assumption breaks. So we have to take a step back to handle the data before this data preparation. Several possible ways that the first to check the distributions using histogram or quartile plot. Yes, if we make sure that the data is abnormal, then we should use techniques to pre-process this data. That is normality-based scaling, for example, non-parameter scaling, and also quartile transformation. We can map the data to a uniform or normal distribution. Scikit-learn provides something like a quartile transformer like this, and you can, if you have the abnormal data, data is not normally distributed, you can use this one to do a transformation before the training. And the second option is that to transform some screwed data, just a part of the data, and also using the power transformer provided in scikit-learn. This is also a possible way to transfer this part, and then you plot this data, make sure that after this transformation, this data is kind of normal or kind of follow some kind of distribution before the training. Usually we follow the procedures like this to pre-process the data, but this is kind too project dependent. I cannot say which is the best for your project. But keep in mind that if the data is not normally distributed, take techniques, using the regular techniques to pre-process data. You need more time to pre-process data and to make sure that you can get well-structured data before the training. Yes, we talk about the one of the two tasks in supervised learning, that is classification. Classification is a type of supervised learning where a model can learn to put things into categorical based on the features. We can have binary classifications, like the model can choose between two options, like yes or no, turn left or turn right. Multi-class classification is when there are more than two categories, like we sort the images into cats, dogs, and birds. So representative algorithms like instance-based, like KNN, we talk about this, probability-based, hyperplan-based, or we can say this is margin-based method. It's a tree-based or network-based method. In this episode, we will cover these algorithms from this method. So we will pick up the representative algorithms to build and train the model, and then evaluate the model's performance in classifying penguins into three species. All right, we come to the data preparation part. I will switch to the Jupyter notebook right here. So let me go through this. Import the necessary packages, for example, NumPy, matplotlib, and the pandas, and also Seaborn. We load the data site about the penguins. Working these penguins, 4 categorical features and 4 numerical features. We describe to get the statistical information, and then we have this pair plot. Section 2 become data preparation, we handle missing values. But first, we need to drop the row containing missing values just for keep the simplicity. And the second, we check if we have duplicate. If yes, we will remove this. But currently, we don't have duplicate. It's good. Third step of encoding the categorical variables, because we are going to use these space aligned these physical parameters for this prediction and also the training. So we categorical all these encode these categorical variables to numbers. Male is 1, female is 0, and we don't have none right here. After that, we will have the data processing, and this we did not cover this yesterday. Before the training, we need to handle 2 things. One, about the preparation, we get well or structured the data. The second is the processing. We need to get features and get the labels and the training and the testing set. So at this step, we will get a species. This is the label we are going to predict from this physical measurement. Then next, we try to split the data into training and testing site. Why for this? We need to verify that the trained model works well on the unseen data. Here we follow this 80-20 rule, which means that the 80% for the training and the 20% for the testing. You can see here 266 for the training and the 67 for the testing. Another step is about the feature scaling. Feature scaling is adjust the range of input features so that they have similar range. We can call it standardization or normalization. To answer the question, yesterday we mentioned that for some data not standardized or not abnormal, or it's not Gaussian type, then we can take more steps to make sure that the data is well behaved before the training. But here, for this penguin data set, it is kind of a Gaussian distribution. So this single step is enough. I should say also that without the scaling, the model may give more importance to large scale features. Like if you see in the physical measurement for the body mass, we have this 1,000 scale, and here for the billions is 10 scale. If the model we gave prioritize this body mass because this value is quite large. Yes, here we adopt this standard scale to adopt this standardization, both for the training and the testing set. All right, data is ready. We can start the training process. Now I will switch back to the lesson material to talk a little bit right here. In this episode, we will try to several mode, KNN, naive Bayes, decision tree, neural network. All these models aim to predict the penguin species from physical measurement, but each use a different way to find the patterns in the dataset. So for all these models, the workflow is almost the same. First, we choose a model class and import it, for example, its neighbors, something. Then we set the model hyperparameters by instancing the class with the desired values. Then we train the model on the pre-described training dataset using .fit method. After this fitting, we can make predictions on the testing dataset using this .predict method right here. After that, we evaluate the model's performance using appropriate matrices. For the classification, we use the score, like accuracy score and confusion matrices. We will like this. For the regression task, we will use RMSD, mean root mean square error, and also the R squared score. And the final step is to visualize this result. For example, plot the confusion matrix over the plotted curve, so that we can see how the result looks like. All right. First, it's about the KNN. So what is KNN? KNN actually is one of the simple and popular methods for classification tasks. This image illustrates how KNN works step by step. We have a dataset, and we can group it in two groups, this blue point and the red point. Now we have a new entry point, this green one, and we want to know which group it belongs to. Here we should predefine a parameter k right here, which means that the number of neighbors we are going to look when we try to make the prediction. K equals to 1 means that the algorithm looks just one closest neighbor to the new entry data. You can see this red point is the closest to this new entry point. So we can clarify that this new entry data belongs to class 2. It is for this red data point. If we select k equal to 3, it is here, which means that the algorithm are going to look at 3 closest data points in the training dataset. You can see we have 2 blue point and 1 red point. This time, which means that this new entry data belongs to class 1. Weird, right? If we choose another value, we can get a totally different result. And if we choose 5, you can see again, this time the new entry data belongs to group 2. Which one is the best? We can test more. Let's come back to the code part. We set up this, we build a KNN model using neighbors equals to 3, which means that we are going to look at the 3 closed data in the dataset and make the decision. Here are the parameters. Yes, you can see more the parameters. Neighbors equal to 3. We specify this, but the others, the model choose the default values. Algorithm, auto, leaf size 30, and yeah, you can n jobs is known. If we say -1, means that this algorithm will take all CPU cores in your computer to run this job. All right, then we make the prediction. Once the model is trained, we make the prediction. I think trained with double quote score right here. I will explain this a little bit later. So then we make the predictions, and then we check the score and the accuracy score if this good or not so good. From the score, it's 0.97. Because we don't know which value we can reach so that we can get the best model. So we can take this reference and compare with the results from the other training models later. We also print the classification report. You can see we have more scores we can choose. For example, precision, recall, F1 score, and support. And we have the descriptions of these matrices in the lesson material. You can go there. This is the step. Then we come to make the confusion matrices. What's the meaning for this? What we can get from this plot? For the penguin classification task, we have 3 species. It means elderly, chain strip, and gentle. So the size of this matrix is 3 by 3. And the y-axis is true label, means this is the true species of these penguins in the dataset. X-axis is the predicted label, means what we get from the model. The first row, there are 28 elderly penguins in the testing dataset, and all these penguins are identified as elderly. Okay, this is perfect. Second row, we have 20 chain-strip penguins in the tested data, and 18 were identified as chain-strip, and 2 were identified as elderly. Still very good if we say this is a 10% error. In the third row, we have 19 gentle penguins in the testing dataset, and all these penguins are identified as gentle. Okay, super cool. All right, everything about this, just some small error from the chain strip species. We take this result as a reference, and we can compare them with the other models, for example, decision tree, logistic regression, and also network-based method to see which model behaves the best. We go on to the logistic regression. This is a quite basic method for classification. Even so, from the name, you can see this logistic regression, but actually this is a classification tool. For binary classification, it uses sigmoid function, which turn the input features into a value from 0 to 1. If the value is above 0.5, and here, and we put this into this class. If the value is lower than or smaller than 0.5, we come to another class like this. For a multi-class classification, logistic regression is extended in 2 ways. First is softmax regression, right here. So this is quite similar to logistic regression, but this method calculates the probability for each class and wants to pick up the highest probability. For example, for one penguin, number 1, we make the prediction from the result is that 66% it belongs to elderly, 20%, 24% it belongs to chain strip, and 10% it is gentle. Then the algorithm will tell us the high score is 66. Then this penguin is elderly. For the second one, it is chain strip, and for the third one is gentle. And always pick up the highest score from the prediction. Another one is one with rest method. It split the multiple binary classifications so that we can perform multiple binary classifications. Each time we pick one group or one class from the data. For the penguins dataset, we have 3 species. For the first time, we pick one group, this is the green, and leave the others. The second training, we pick up this group and keep the others. So here you can see that for this one with rest, it perform multiple binary classification. So I should say that the softmax regression is kind of powerful or efficient if we're going to train really multiple classification. You can just run one time and get the result from there. Switch back to the code part. We build this model using the logistic regression class from the scikit-learn. You can see the parameters. Here I set this random state 1 to 3. Just want to make sure that we can use the same set of data for training. For the other parameters, is just the default. You can go through the document to see what is the meaning of this parameters. We make calculate the score for the training 0.95, okay, a little bit lower than the one we got for the KNN. And if you say the confusion matrix for Adley and the gentle, the prediction is good. And for the chain strip, we got three error predictions right here. A little bit, that's why we got a little bit lower score right here. Okay, this is logistical regression. We come to the another method called naive Bayes. This is another probability-based algorithm. It assumes that all these features in the dataset are independent and equally important. Actually, this isn't always true in the real data, but it makes calculation much easier because they just treat all these features independently. It's quite similar to logistical regression. We get a list of probability and pick up the one with the highest score. But they follow different rules. Here we have image to see the difference, the logistical regression. There is a paragraph about theoretical description. Logistical regression always learns a linear boundary. You can see this is the linear boundary right here to separate this class. But naive Bayes always get non-linear boundaries. You can see this kind of concave, convex. The prediction is based on different criteria. To the code part, the workflow is the same. To build this model, we're using the Gaussian naive Bayes, Gaussian-based naive Bayes from the scikit-learn. Build this model and train the model. Here you can see the parameters. Not so much. And then we make the prediction and also the confusion matrix. You can see the score, it is 0.83. Again, a little bit lower than the score from KN and logics regression. And we can see why we got a quite lower score. It is from here. For the gentle, it is okay. For the J strip, it is also okay. But for Adelaide, it's not so okay. We have 28 Adelaide species right here, but only 17 were identified as and you can see 11 were identified as chain strip. This is not so good. Why for this? Because the assumption is that the naive Bayes assume that all these features are independent. But for the penguins, it's actually not true. Penguins' features are somewhat correlated. Bigger penguins usually have longer flippers and also heavier body mass. This is intercorrelation between these features. For the other dataset, if there's no explicit correlation between features, you can use this method for the classification task. And I should say that the training is quite fast because this model treats all these features independently. In these sections, we talk about logistical regression, and we create a straight line better to separate the two classes. But we got issues. This works well usually if we can separate these two classes by line. But if with that we have two classes, they are well separated, means that there's a large gap between these classes. I cannot say if you say separate the elephant from ant, this is unfair, but you can separate cat and dogs. We see there's be a large gap between these two groups. We'll see how does this happen. There will be many possible straight lines. We want to separate cats and dogs based on weights and ear length. And this might be dogs, this is cat. You can see we have multiple lines right here. Which one is from the logic regression? It is the red dot dash line right here. But the green is also works, and the blue and this yellowish also works. this, you can see that each line we can get a clear separation of these two classes. But here is the question, which is the best one? How can we pick up the right one for this classification? And so that we can have a better prediction on unseen data. In such case, we sort to SVM, which is called support vector machine. It is a margin-based or hyperplane-based method. Here is one image to demo the concept of this SVM. We have a linear boundary from the logistical regression. Then we pick up examples. And here I pick up 4 data point near the boundary. See, for this group, it's 1, 2, 3, 4. For this red dot, for the cat, it's 1, 2, 3, 4. Definitely, you can pick more. This 4 points form a support vector. And see, we have 2 support vectors right here. For each vector, we can draw a line, which is called hyperplane. This is for the red data point. This is for the blue data point. The core concept of SVM is to maximize the distance between these 2 parallel hyperplanes. Maximize the distance between these 2 lines right here. So the SVM will not look at all these data points. It just focus on the data point near the boundary part. Here I picked up before. You can see there are lots of data points right there, but that is far from the boundary part. So the SM algorithm, SVM algorithm will not take care of this data point into account. So this makes this classifier more stable and reliable because it just focuses on this local area, especially when the classes are well separated and it's less affected by the outliers. SVM, it is here. We use this SVC from this second. SVC is short for support vector classifier. For this classifier, we use these hyperparameters to construct the model. Here we use the kernel RBF. This function will introduce some nonlinearity between these features. So that is why this SVM or SVM algorithm can capture the nonlinear features between nonlinear issues between features. 2 parameters C and gamma. So C controls the trade-off between margin and noise and also the classification errors. A smaller C leads to a wide margin, or larger C we have a narrow margin. So that makes sure that this will have a direct effect on the model's prediction. Gamma controls the shape of the boundary. We train this model. You can see the parameters, a long list, not to discuss this, talk this one by one. And we make this prediction and also print the accuracy score. 95 seems good, and we can visualize from the confusion matrix. Okay, Adelaide is okay, gender is okay. The only thing about the chain strip, we got the 3 errors. That is, let's say 50%. Still good. Until now, we have worked on several method algorithms, instance-based, that is the KNN, probability-based, that is logic regression, naive-based, and also the margin-based SVM. We will go further to talk about the tree-based and also the network-based algorithms. Tree-based, what is the tree-based algorithm? This algorithm is kind of intuitive from these figures you can see. It's easy to understand. It splits the data step by step based on feature values. So that it formed a tree-like structure that separates penguins into different classes. Think of it like this. You are kind of driving along the road and coming to the intersection. You have 2 choices. You can make a decision, go left or go right. Then you come to another intersection, go left or go right. The intersection is a kind of node right here. So each decision will narrow your possibility route to somewhere, let's say, go home. In this example, each intersection represents a node right here with some features, and each possible term corresponds to a branch. Here you can say this is go left or go right. And the final destination represents the classification outcome. We have an example to separate cat from dogs. Suppose that the cat have two features. One is ear length, the other is weight. We can use one tree to separate this. This is quite clear and understandable. But if we have three features, for example, we have weight, ear length, and also the tail length, then we can sort to two-layer tree structure like this. But if we say the visualization, it's kind of difficult to visualize. But the concept is the same. For the first time, they split this tree into two leaves based on some sightings at the node. And the second, we can have another splitting of this data. Then we come to the final class decision tree. Yes, we construct this model using the decision tree classifier from scikit-learn. We specify that the max depth of this tree is 3 layers. We make the prediction 94, okay? And then the confusion, okay, gentle is okay. Oddly, we got one wrong prediction. For the tree strip, we still got 3 wrong predictions, kind of comparative to the previous one, but from VSVM, spot vector machine. Here we can plot the tree structure. There you go. You can see from each separation, this is the information based on this. The data are split into 2 leaves. This is the flip length is less than 0.339, and the sample and the value is here. After this separation, we can see the bill length is smaller than this, and the bill length is larger than this. And then we can have another separation. Island is something, and the sample this. Yeah, each time we based on one feature or one criteria and separate the samples into 2 groups, and gradually until now we set this tree into 3 layers. Max depth is 3 layers. I mean, after this one, we can get the results about the penguin, the classification of penguins into different groups. Okay, I should say that the decision tree is easy to understand and visualize, but it has some downside. A big issue that we should set the max depth for this tree. If this number is quite large, means this tree will go deep, very deep. This means that the algorithm will learn noise and the training data instead of the real patterns. If it is too shallow, means we keep it 1 layer or one max depth is 102. The algorithm cannot learn too much from the data. So it's that this value is too critical. We have to make a good selection. In addition, this algorithm is kind of sensitive to small changes in the data. Because just a few noisy measurements can create a very different tree structure. So that makes this algorithm less stable. Yeah, to fix this issue, we come to a concept of ensemble learning. It's here. What is ensemble learning? Ensemble means we combine several weaker models to make a stronger one. We combine multiple trees together and make it as a kind of forest. The idea is one weak model might make mistakes. A group of weak models is more likely to be cracked. Okay, the idea is okay. There are 2 main types, means bagging and boosting. What is bagging? Bagging means that each weak model in this ensemble is trained independently. One tree will train the data, a small amount of data. The other tree will train on another small amount of data. Then the predictions of all trees are combined together to pick up the right class for each penguin. An example is random forest. That is, we put lots of trees together. Another method is boosting. Boosting means models are trained sequentially. This is random forest. We have a lot of trees, and each tree will train on a small amount of data independently. The third part is boosting. Boosting means that the model is trained sequentially. We first train the data using this tree, and after we get to the result, we have another tree, and the tree train on the trained data. Though that the second tree will make some corrections if based on the data from the first tree, and then sequentially we make the training sequentially one tree after another. This is called boosting. A representative boosting is gradient boosting. So in this episode, I think 50, I don't have enough time to go through these two algorithms one by one, but I would like to leave this to you as exercise. If you could come to the code part, you can see 4.6 is random forest, 4.7 is gradient boosting. These are two example learning method of decision tree, and you can see which one is better than the others. And if you compare the result from the other with the other models like logistic regression and also SVM, you can see the difference and the performance of these models. Finally, we come to the last part. We start with a multi-layer perceptron, or to the MLP. MLP is a simple kind of neural network made up of several connected neurons. Now here is just one neuron right here. That structure is designed to mimic the human brain. For this neuron, and it has several numbers as input. Here, this input x1, x2, x3, xm, we have n input. For penguins, we have four numerical input, numerical features, and two categorical features. We have six input. And it has one output. We want to predict the species of this penguin. It's just one output. So each input have a weighted number, W1, W2, and Wn right here, and we should calculate the weighted sum of this input. So the first step, we should calculate the weighted sum, xi times wi right here, and the summation of this. And the second, we add the biased term. Biased, it is here. And the equation, this is a step. Then we apply an activation function to get the result. One thing I should address, what is the activation function? Yeah, activation function, this is a mathematical transformation to convert the data from one to another form. You can think this is the add linearity to this model, which enables the network to learn some complex patterns from the data set. Here are some representative form of this activation function. Sigmoid, we came to this before, and linear activation function. This is just output the input as it is. It can be considered as a reference. It doesn't add any nonlinearity to this model. Tank is quite similar to the sigmoid, and the other one is Lulu. It's an abbreviation of rectified linear unit, and the output is 0 right here if we give negative input, and it keeps the positive input right here. It is quite popular. This activation function is widely used in lots of algorithms, and also in different frameworks, PyTorch, TensorFlow. Yes. Later, when we construct this network, we see we use ReLU. But this is just for a single neuron. We can call it a perceptron. A single perceptron or a single neuron can only learn some simple patterns from the data set. And then a natural thing is to combine multiple perceptrons together. Okay, this is the ensemble learning we mentioned before. Then we call this multi-layer perceptron. This is where the MLP comes from. Here, example, it consists of 3 layers: input layer, output layer, and one hidden layer in between. In the input layer, we have 3 neurons, and hidden layer have 4, and the output layer have 2 neurons. Each for the input layer, it receives the raw data and sends the data to the hidden layer. And the neurons in hidden layer can process this data and gradually extract some high-level features from the data. And the output layer produce the final prediction, like labels for classification and the number for this regression. This is the theoretical description. This is the code part. Let's switch to the Jupyter Notebook. Multi-layer perceptron. And this is, we use MLP classifier to construct this model. We use multiple hyperparameters right here. For this model, I build a 3-layer perceptron. For this MLP multi-layer perceptron, 3 layers, one input layer, one hidden layer, and one output layer. For the hidden layer, it has 16 neurons. And for the input layer, it has 6 neurons, I should say, because we have 6 features in the penguin dataset. And for the output, we have 3 neurons and 1 for each penguin species. And here are more hyperparameters. Activation function, we use ReLU. Adam is an optimization algorithm that updates the weight. We should update the weight parameters iteratively so that we can get a better fitting. Batch size equals to 8. So each time we in the machine learning or this machine learning or in future if we want to learn about deep learning, each time we don't send the whole data to this model for training. We send a small amount of data for the training. During the training, we send another amount of data. After the training, the model will automatically take the data in the waiting area. And the size of this small amount of data is called a batch. Batch size is a number of samples in the batch. And also here we set the learning rate constant and the initial learning rate 0.001. So we want to keep the learning rate constant during the training. A small value right here will indicate a slower training, but it's more stable. Max iteration is the max number of iterations for the training. Build this. If we click this, we can have a detailed list of all these parameters. Hidden layers, activation, ReLU, solver, batch size, max iter, random state. Yes, this is the long list for these parameters. And actually, we can get more information about the model if the number of layers, if you click this one. Yes, you can see the number of layers were 3. The number of neurons in each layer, we have 6, 3, and 16 in the hidden layer. All right, then we train this model on the training data side. We can get what's the score 1.0. It's 4 score. Why this behaves so good? If you see, idly, chain strip, gentle, it's perfect. For each species, we can get the full prediction on the training, on the testing data set. You got the full score, right? This MLP is at least now it is the best model we can choose on this penguins data set. MLP is just a neural multiple layer, usually has one or two hidden layers. We continue to the DNN part, which is deep neural network. Okay, we still start from MLP. This is kind of basic neural network, usually with one input layer, one output layer, and one or two hidden layers in between. But it's a struggle to learn some complex patterns. For the penguins data set, it works fine. But if we have a large data set, quite complex data structures, the MLP may fail. To handle this, we can use a deep neural network, which is basically MLP with many hidden layers. These extra layers can help the model to learn this step by step. So in the this is I should say this is the territory for deep learning. I don't want to talk too much about this. We have a course about introduction to deep learning. We will run this course each year, so pay more attention about the training arrangement from us. Here I provided the code examples. I use the Keras in TensorFlow to build this deep neural network. Or before that, I do some data preprocessing. And you can see I build a neural network composed of 5 layers. I have a summary from about this deep neural network, if you see. Yes, we have one input layer, we have 3 hidden layers, and 1 output layer. For hidden layer, this is hidden layer, the first hidden layer, the second, the third. For the first one, we have 32 neurons. Second, we have this is the first one. We have 32, and the second we have 16 neurons, and the third one we have 8 neurons, and the output we have 3 neurons because we want to get the 3 output from to correspond to 3 classes for the penguins. Totally, we have 851 parameters. I think this is quite small if we compare to GPT-3. Yesterday we talked about. For that GPT-3, it has 175 billion parameters. That is. Okay, here I use the parameter the dropout. So what is dropout? If you switch back to this right here, it's a regulation technique to reduce overfitting, to avoid overfitting. The model randomly drop out some connections between neurons. If you can see the connection between the second, the green part second and the first blue, there's no connection right here. It means we drop out this connection between these two neurons. And for the third one, there's no connection of this green to this blue. This means we drop out this connection. Randomly drop out this means that we will keep some randomness so that to avoid fitting during the training. Here I use Keras or TensorFlow to construct this deep neural network, but you can work on this classification task using PyTorch. We have the information of this model. Then we compile this model before the training and train this model. We get an object about the history which contains the training information. And if we plot this one, we can see the loss or epochs or training progress. How the loss is similar to the accuracy score. Is we want to minimize the accuracy score, and Yeah, this is the training. It's mainly related to the deep learning thing. So I'm not talk too much about right here. Yes, we can have a short summary about this. For all these models, they have KNN, logistical regression, naive Bayes, and supported vector machine, decision tree based, decision tree, random forest, gradient boosting, and also the network based algorithms. I print the score, accuracy score for each model I've got during the training. From here, you can see that multi-layer perceptron is the best one. We got the score 1.0. For the neural network, the 0.99. No problem. For this naive Bayes, it's the lowest one, 0.84, because it assumes that the features are independent. In fact, it is not true. But here you can consider this naive Bayes as the example just for the exercise. In your project, you may select the right one, the right algorithm for the training. If we plot all these confusion matrices, again, you will see the difference. This is MLP. We have a full score right here. For the others, we can get some errors, predictions, this naive Bayes. Yes, I think I can stop here. We have 20 minutes for the exercise. Let's continue to the second episode today to talk about the regression. Regression is to predict a continuous value from the input features. It is a real number. It is not a categorical variable like yes, no, go left, go right. It's a number like 1.8 million if you want to get a loan from the bank. It's like a body mass for the penguins. The penguin state set, I should say the penguin state site is always used for the classification, but we can also try to use it for the regression task if we can pick up a continuous target right here. This is the pair plot based on species. If you see which pair is the most optimal, this might be, this doesn't work, this doesn't work, this might be okay. This is the flip length or body mass or flip length. They're the same. We can see if we ignore the colors of this data point, it's kind of linear, right? So we can pick up these two features, body mass and the flip length. We want to predict the body mass from the flip length of penguins. These are two features. So body mass is the label and the flip length is the feature for this new task. Procedure is similar to the previous episode. We will experiment with multiple algorithms, let's say KNN, linear models, nonlinear models, tree-based, that will be decision tree, random forest, gradient boosting, and the neural network based, for example, MLP, multi-layer perceptron, and deep neural networks. For this deep neural networks, we provide the samples here, but we're not going to talk too much about details for this deep neural network thing. That comes to the deep learning. We will validate this model's performance using matrices like root mean square error, RMSE, or R squared score. And we will also plot the predictive curve for the visualization to see how the predictive curve looks like. For the data preparation and the processing, again, we always start from here. Let's switch to the notebook. We import the packages, numpy, matplotlib, pandas, seaborn, and load this data from seaborn. Plot this pair plot, see how it looks. And data processing, we drop the rows with missing values and also check a duplicate. Here I don't want to handle outliers because I know that there is no outlier in this data side, so we save some time. and then we split the features. The feature, this is the flipper lens, this is the one feature as input. Body mass is the label as output, which means that we will predict the body mass from the flipper lens information. Feature scaling, this is the question proposed in the shared hackathon that we can use one standard scaler. Basically, if your prediction is a category variable, but if the category, the prediction is a numerical value, the label, the feature is also a numerical value. We should use 2, because after that, we should use the inverse transformation. After the prediction, which the inverse transform the data to the original feature like range. That's why we have to use 2. Otherwise, you make it messy. You can test it. You just use one standard scaler, scale it, and later inverse transform the data. You will see how the data looks like. It is scaling, splitting, training, and testing. We'll see. Here are the distribution of all 333 data. The green data for the training and the orange for the testing. We use this kind of data for the training and also testing. And also we will plot the predictive curve and see how the fitting curve looks like. Data is ready. Let's come to this training. First is KNN. Again, it's KNN. It's a lazy learner. It's not a machine learning algorithm. It just memorize something and do the prediction based on the distance values. And here is the KN neighbor regressor to build this KN model and to fit this model on the trained dataset. As the neighbors, here we choose 5 neighbors, and the other algorithms, the auto leaf size and the end job is known. It means that we just use 1 core for the training. If it's -1, we will use all these cores in the computer for the training. We make the prediction on the testing set and evaluate the performance. Here we use 2 matrices. One is RMSE, means root mean square error. This specifies how the prediction looks like, and we also have another one is R square. Root mean square, or okay, the RMSE, it tells us how far, or on average, the predictions are from the actual values. The R square score tells us how much the variations in the target, body mass right here, is explained by the model. To show how the KN works, let's plot the predicted curve. All right, you can see quite a piecewise smooth right here. But how to crack this curve? Okay, let's say we have a penguin with the flipper length of 200 right here. So in this data site, they will search, okay, which penguin has the flipper length of 200 or quite close to 200. That means the calculation, the distance of the penguins. So we will pick up the 5 penguins with their flipper length quite close to the target, to this penguin, unknown penguin. And then once we pick up the 5 penguins from the data site, we know their body mass. Then we calculate the average of their body mass. We get 1 value. This value is right here. And we can get a lot of samples, like the flipper length of one is 180, 190, 200, 210. We get lots of predictions. We link all these scattered points. This is the predictive curve we get from the training, from the learning. Right? It's not. I hope it is not difficult to understand about this. But just let me know if you're confused with some point. So you can see that the predictive is kind of piecewise smooth. Here is just we choose k equals to 5, means we are going to look for the 5 nearest penguins in the dataset with a given flip length. But if we choose 1, we choose 7, what it looks like. I have this plot in the lesson material part. You see, k equals to 7 means it's fluctuated too much because it's just want to look for the 1 with closed. And there are lots of fluctuations because of this. It's not so much. If we choose k equal to 7, it's quite smooth because for each flip length value, we can get to the 7. And if we take an average, it's changed not so much. That's why you can see this red line here is piece smooth, and for this purple is stepwise. It's not smooth and reflected too much. Again, the choice of k values is quite important, and you have to make multiple predictions to see which one can give you the best prediction. As I said, you have the labels, you know what is right and what is wrong, then you make a decision. You can make the decision like this. If we don't have the labels, we don't know what is true, what is false, then this is not a regression. This is the clustering thing. We'll talk about that tomorrow morning. We know, we said it before, KN is a lazy learner, and KN does not have learning process. It just stores the entire data set and perform natural computations at the prediction step. If the data size is quite small, I mean for KN it's okay. You need quite a small amount of memory to store all this data. If the data size is quite large, it is not applicable because it will need a large memory to memorize everything and then calculate something during the prediction step. So I should say that we cannot rely too much on this prediction. It's just the entry level for you to know about this algorithm. The following part we switch to the basic linear one, that's called the linear regression models for the prediction of penguins body mass from the flip length. That's the linear regression. This is the linear regression task. This is distinct to the logistic regression we mentioned around 9 o'clock. Okay. This model will find a single straight line that best fit all data. And after fitting, we can get 2 parameters. This is the coefficient and the intercept. We train this model on the training data side, and we get the value. This is the coefficient. This is intercept, and we get the score for MSE. It's 411. So R squared is 0.72. Okay, we can see how can we make a comparison with the values from the other models. We plot this linear curve. You can see this is the fitting. It looks okay, but we want to know residue analysis. What is a residue? Residue is the difference between the actual value and the prediction by this model. This is one. Let's say this is 178. The prediction is this value. We know this value on the because it's on this curve. We have the coefficient, we have the intercept, we can get the value from the equation. But the true value is here, like this point, this orange point. And the difference of this y value minus the prediction, the prediction, that is the residue for this sample, I mean for this penguin. For all this data in the testing site, we calculate the residues. And here it is, the residues here, and this is the for fitted values predicted the body mass, the gram. You can see how it looks like. From here, I can see the residues both for the fitted values, like the body mass and also the flip length. It is scattered randomly around the array. around 0, right? There's no specific patterns, clusters right here. I can say that this linear model is kind of unbiased, and that's a good job for this prediction. And it can capture essential relationships between the Philippe length and the body mass. We can have more. The Thus conclusion is also supported by the distribution of these residues with this histogram. You can see the distribution is kind of symmetric, bell-shaped, and centered around the 0. Okay, well, that's why we can say this fitting is good. And also for this quartile plot, we can see the normal distributions is also with the residues. This means verify that the distribution is Gaussian-like based and without any biased prediction from here. Later, when we use another model, we will see polynomial regression with the degree equal to 5, we will see a shift of this histogram to the left. That is kind of overfitting. Here, we calculate RMC on the testing set. This is useful, but we want to say this is kind of the half of this story. Well, we want to get a full picture. We need to calculate these values, I mean RMC and R squared scores on both training and testing set. Here is the result. You can see for RMIC it's 387. For testing is this 411. If we say that the 387 is really smaller, for sometimes we can say this kind of comparable, not significant difference. But if we really say that this number is smaller, really smaller than 411, then this really matters. We can say this is model has kind of overfitting because it's a little bit smaller. In order to fix this issue, we have two methods. We switch back to the lesson material. This is called overfitting and underfitting. And it really matters. And we have more algorithms to extend the linear regression. That's what we call the regularized regression models method. That is Ridge or Lasso. We keep this as an example. You can test later. But describe a little bit about this. So Ridge and Lasso regressions are proposed to extend the linear regression to minimize the overfitting. These two methods have different regulations, like R1 regulation, R2, to focus on different part. I am not going to talk too much. In the x-axis, you can see that this is the code example. We have this Ridge regression, this Lasso regression, and we train the two models on the same amount of data, the same training set. We can get these predictive curves. For this regulator, for the Ridge, it is this red one, quite close to the linear prediction. For the Lasso, this 0 point, we use this alpha, this different value. Alpha means the different regulations. A small alpha, we have a strong regulation. It's large alpha, we can have a loose regulation. That's the one. Loose regulation, we can get quite close to the linear regression curve. Yeah, take step for this exercise later, and you will see how to get the result if you tune this alpha parameters from 0.1 to 1 to 10 to 100 to even larger. We will follow the linear regression and go further to include some non-linear issues. If we think that there are really some non-linear issues in the body mass and the relationship between body mass and Philippe length, this is called polynomial regression, and which will model the penguin's body mass as the polynomial function of Philippe length. This will let the model to fit it's not a linear curve, but a curved relationship between this feature and this label. We come to this code part to see how it looks like. Polynomial regression. We use this polynomial feature from this scikit-learn. Here we choose 2 degrees means equals to 3 and equals to 3 and equals to 5. What does this mean? We fit this model. If we say this is the first and this is the second term, this is the third term, and the fourth term, the fifth term, the higher the term means we consider more the nonlinearity between these two, between the feature and also the label. Let me see if we choose degree equals to 3 and equals to 5, we will see the difference. For degree equal to 3, this is the coefficient 0 for the zero part 1, 2, 3. This is the intercept. We got the RMC is 407. Okay, this is quite good. If we remember that for the linear regression is 411, this is 407 means this one is a little bit better than the linear regression. For this one, which degree equals to 5, get this one, the score is 415. Okay, a little bit worse than the linear regression, but we will see how the predictive curve looks like. You see, this means that the nonlinearity is really included in this model. The red curve for this degree equal to 3 and the blue for this equal to 5. From here, it's difficult to figure out what is the difference. This one, if we have more data analysis, okay, for this this is the linear regression I just showed minutes ago. You can see the distribution of this curve is kind of bell-shaped, kind of symmetric, and the maximum is 0 center right here. But if you see degree equals to 5, I would say that there are some clustering things, patterns right here. And if you see the peak is around a little bit shift to minus 200 something. It's a little bit shift of this peak to the left part. This is the kind of signal of overfitting. Actually, when we use polynomial regressions, the main issue is how to choose the right degree. This is also applicable to the other models. How can we find the more optimal hyperparameters for this? A better way is that we use evaluation techniques like cross-validation, like a grid search to find the optimal degree or parameters before this. But this is another task. We can have this later. We have this support vector regression part. We use a grid search and cross-validation method to find the set of optimal parameters from the testing. Okay, this is for the linear regression and also the polynomial regression. We'll make a comparison. If we add a little bit nonlinearity, let's say degree equal to 3, it is good. We can have a better fitting. If add more like a degree equal to 5, this is not good. Then we come to another model called SVM. The central idea of SVM or SVR is to maximize the distance between these two parallel hyperplanes determined by the support vectors. Support vectors are the point that are close to the fitting lines. Instead of manually add polynomial features, so SVR will use kernel functions. This kind of kernel functions will capture some nonlinear issues in the data set. So this is a comparison of SVR and the polynomial regression. For this polynomial, we add these terms one by one. Okay, if we don't know which one is the best, we have to test more degrees, like degrees to 3, 5, 4, 6, 7, I think. But for SVR, that's not necessary for us to do so. We can just use one kernel function, and this function can capture these nonlinear issues in this pattern, in this dataset. Here we use another called RBF. We used this before, and here we will again use this one. And definitely we can choose the other kernels, for example, linear kernel, polynomial kernel. This is RBF, I mentioned this. So, but, you can make a test to see if you choose RBF, the nonlinearity is included right there. But if you choose linear or polynomial, you see what kind of content is included in the model. Let's come to the code part. Okay, we build this model using SVR, kernel equals to RBF function, gamma, and C. We mentioned this before. We fit the model on the training side and make the evaluation. The score is 433. And this is not good, right? For the linear, it's 411 and 411. For the polynomial term with the term, even with the degree equals to 5, we got 415. But this SVR is even worse. It's 433. Let's see how the predictive curve looks like. Make a comparison with the polynomial term is degree equal to 3. But from here, it is a little bit shift to the upper part. If you say that this blue curve is all above this red curve, that might be the info for these fitting results. Oh, actually, I mean, ideally, SVR can do a better than linear regression if we say that the relationship between body mass and the flippiness is really non-linear. But here we get the reverse, means the penguin regression task SVR with the RBF kernel performs worse than the linear regression and also the polynomial regression with the degree equals to 3. The main reason might be that first, the relationship between flippiness and body mass is mostly linear. There's no necessary, or you can add some nonlinearity, but with mild nonlinearity. You cannot add too much. And second, the hyperparameter is not optimized. Here you can see that when I construct this model, I just pick up randomly gamma equals to 1, 0.1, and C equals to 100, and make the training. This is definitely not the best it's the best parameter hyperparameters for this model. But how can we choose, or how can we determine a set of best parameters? We use greatest search and cross-validation. This we use two techniques that this will enable us to find the best set of optimal best set of parameters for C, gamma, and also epsilon right here. Here you can see I provided several parameters. One C, I can choose. I can pick another one. 0.1, 110, 100, and 1000 to see. For gamma, is still the link. I can add more like 100 something. And for the epsilon, we choose the parameters. For here, I use a 5 for the cross-validation technique. It is described in the lesson material. For this, it is the greatest search to find a set of hyperparameters that can give the best score. If I run this, it take time. We have 5-fold. We have 75 candidates, totally 300 fitting like this. And then the best parameter found is C is 1000, epsilon is here, gamma is here. We know that this hyperparameters is the best one for this penguin dataset. Then we can use these hyperparameters to construct this model for the training. And you see, for the SVR with a random, from the beginning, this RMC is 433, but with this optimal parameter, hyperparameters is 421. Okay, a little bit increase. Here is the way to show you how to find the optimized parameters, hyperparameters, if during the we want to improve the model's performance. This okay, this is quite close to the polynomial regression with the degree equal to 3. It's reasonable. Yes, this is the polynomial regression. Then we come back, we can continue to the decision tree method for the penguins regression task. Directly come right here. For the decision tree, we build two models. One with the max depth equal to 3. We want to focus on 3 layers tree. The other one is max depth equal to 5. We build a tree with more depth, means that we might come to something about overfitting, but we'll see if we can get that. We train the models, the two models, make prediction. This is 1, 2, and the predictive curve right here. We can see that these predicted curves are piecewise smooth, I can say. This is similar to that obtained from the KNN. In addition, tree depth is also an important parameter right here. Models with shallow tree means depth equal to 3. This red curve, you see, has a very few split and may create a very broad region, did not fluctuate too much. The model with a deep tree means depth equal to 5. This is the blue right here. It has a more split. You can see lots of fluctuations right here, and which may increase the risk of overfitting. So this model can produce the overfitting or not. We can calculate the RMSE on training and testing set and make a comparison. If we say that they are really overfitting from this decision tree, how to resolve this? We can use random forest, we can use gradient boosting to solve these overfitting issues. Like this, random forest and gradient boosting regressions as exercises for you to test. The code is right here. You can see this is random forest, and this is the gradient boosting. And yes, later we can make a final comparison. Linear decision tree, random forest, gradient boosting. It may be worse than the decision tree. One critical issue is the size of this dataset. In this penguins dataset, we only have 333, effective penguins for during in the dataset. If we split like 80 for the training, 20 for the testing, we only have 267 for the training. This is really small amount of data, and here is just one feature, right? Quite limited data here. If you really have a large data set, you can see how the prediction looks like. Definitely in this one, we can use view length, view depth, and also flip length to predict the body mass. But that is optional. You can test that, but you can combine all these together to make the prediction of body mass of the penguins. All right, we come to this multi-layer perceptron. Again, we use the scikit-learn to show this. And in this work, we'll try to build a neural network model using scikit-learn, and also provide the code examples to build the model using TensorFlow and using PyTorch. And you can see that in scikit-learn, the same, procedure is the same. And the hidden layer, here I use the 3 hidden layers. The size is the first hidden layer. It has 32 neurons. The second hidden layer has 16. The third layer has 8 neurons. For the activation function, I use ReLU. For solver, I use Adam. And for the max iterations, I use 5,000 steps for the training. click it, it's quite fast. You can see the RMC for this MLP is 416. Kind of good, quite close to the value obtained for the KNN, for the linear regression. And then we see how this predictive curve. And actually, you can play the code. For example, this we use TensorFlow, construct the same neural network, 3 hidden layers. That's why we can make a direct comparison. 3 layers, 3 hidden layers. The first hidden layer, second hidden layer, third hidden layer. We use the rule as activity functions. And this trained model is the batch size. We mentioned this before. And the epochs, 200. You can say epochs for the training. Yes, you can see. The loss function is a characterization to see we want to how this training model behave. We want to minimize the loss. It is done. Let's see. Okay. Then we plot this loss with the number of epochs. You can see gradually decrease. Then we see what is the predictive curve. It's quite close to the one we use scikit-learn. And if we perform another one using PyTorch, you will see it's identical, almost identical, right? Because this one we build a similar, or similar, it's almost the same neural network for the training. All right, short summary, a comparison of all these training models. Here I plot all this because some trainings I did not perform, so I cannot get some values. And here just to show you what I got if when I run all these numbers yesterday. For different algorithms, let's say KN, linear regression, regularized regression, ridge, lasso, you can see how this looks like. And this is our MSE score, and this is R squared score. And yes, I should say that for each, if I make a comparison, it can compare to the RMSE, this one with polynomial regression with degree equal to 3. They gave the lowest RMSE, the 407, and the highest R squared, this is 0.73. Yeah, slightly outperforming the linear regression. You have several strong performers, for example, linear regression, ridge, polynomial with a degree equal to 5, this, and also the neural networks from MLP, from Keras, from PyTorch, they will be quite good with relatively low RMC scores and high R squared score. The moderate is random forest. Random forest, this one is 420 something. And this is decision tree with the depth equal to 5. And also we have this one with the structural vector regressor and even the optimized one. And this which means that we have space to improve the model's performance. The weaker performer is like this one, KNN, and this is regularized range with ridge. Maybe that I did not set the optimal parameters for the training. You can find a set of optimal parameters, and you will get a better score for this ridge. And this is structural vector regression, and this is for the gradient boosting. Okay, how to find the set of optimal parameters for each algorithm? The procedure is the same using grid search and also cross validation techniques.